In this video, I'm going to introduce you and define the kinetic energy and also work energy theorem. So just like the momentum, when the object has a motion, it contains some kind of a momentum. And also it contains energy. And that's called kinetic energy. Any moving objects possess kinetic energy. Kinetic energy. Kinetic energy. Moving object possess energy. So again, like a momentum, when you have a object that's moving, it possesses some energy, and the kinetic energy is 1/2 times mass of the object. So the bigger the inertia, bigger the mass is, you have more kinetic energy. Then also speed or velocity square. This is kinetic energy. Again, kinetic energy is 1/2 times m times v square. That's the definition of kinetic energy, how much you can measure. Kinetic energy is also the same as gravitational potential energy, elastic potential energy, work. It's a scalar. And we use the joule to measure. So here, 1 joule can be 1 kilogram meter square second square. And that's also same thing as a 1 Newton times meter. They're all the same thing. So as I said, bigger the mass, bigger the kinetic energy. You're moving faster, you're going to have a bigger kinetic energy. Kinetic energy, KE, kinetic energy, bigger the speed, bigger kinetic energy. All right, so we mentioned in a previous video, we talked about the importance of a zero gravitational potential energy. Zero gravitational potential energy is insignificant. It doesn't mean anything. How about this? When kinetic energy equals 0, what does it imply? Can we have a kinetic energy equals 0? Zero kinetic energy means, it just means that this time it means something. It means that it's at rest. It's not moving. Velocity equals 0. Speed is 0. All right, so kinetic energy equals 0 means something. It means that an object is not moving, it's at rest. Gravitational potential energy. Can the gravitational potential energy be negative? Yes, it can be negative, right? Because you can put 0 of a gravitational potential energy anywhere. So if you're under the 0, below 0, you're just negative. So it can be just 0. How about kinetic energy? Can we have a 0 kinetic energy? Negative kinetic energy? No, never. Never negative kinetic energy. We cannot have a negative kinetic energy. It can never be negative. Why? Because it's 1/2 times mass times speed square. That's square, right? It's this. Mass cannot be negative. Velocity can be negative, but it's squared. Square can never be, unless, imaginary number, you cannot be negative. So kinetic energy is never negative. It's always 0 to positive, some kind of a value. And it's a scalar. It doesn't have any information about moving in which direction. Like momentum, it matters which direction you're moving. Kinetic energy is just how much, just a quantity. And it can never even be 0. So pretty good. What if when we have a change in kinetic energy? So let's say we have an object that's moving with the velocity 1 at that time, and then it changes its velocity, v2. For the velocity to change, that means you have a change in velocity. By following the definition of acceleration, acceleration implies the change in velocity per time, how fast the velocity has changed. So you're going to have an acceleration. It's accelerating. That's why you have a change in velocity. So that means that whenever you have a change in velocity, when you have a change in kinetic energy, right? Change in kinetic energy implies that change in velocity. This implies change in speed, change in how fast it's moving, change in speed, change in velocity, change in speed. And then that means it has to be accelerating. It could be decelerating, it could be accelerating, but whenever you have a change in speed, it has to be accelerating. That means you have, by following the Newton's what law, that you need to have, about following the Newton's what law, that you can say non-zero net force. So what is the Newton's law that we say? If it's there, you have a non-zero acceleration, you're going to have a non-zero net force. So that means that you're going to have acceleration means you can have some kind of a non-zero net force. So, and it's moving. So work here, remember, work is force times distance. That's parallel to each other. And the total work, right, if it's done by net force, and this is the total work. Whenever you have a net force applied, you're going to have change in kinetic energy. Because whenever you have a net force, it has to accelerate. So you're going to see that things has to change the kinetic energy. So this is called work energy theorem. Work done by the total force is equals to change in kinetic energy. and I am saying is that this work that I'm talking about is work done by the total force, net force or total force is the total work. Total work means whenever you have a total work, that means you have some kind of a net force. When you have a net force, you have to have a change in kinetic energy. So, and then a work energy theorem says that whenever you have a change in, you have a work done on the system. So here, it's putting all the work in an energy relationship. If work done on something energy of that something changes. Right? So we say work done by the gravitational force changes the gravitational potential energy. Work done by the elastic force changes the elastic potential energy. Work done on by total force changes its kinetic energy. So work is the change in energy. And let's say if, in this case, if example, if V2 is bigger than V1, then it's an increase in kinetic energy. Then that means that positive work done by the net force. Net force was applied and then it moved in a distance d. So therefore, in V2, the final velocity is bigger than the initial velocity. So you have, whenever you have a, so in this case, the kinetic energy is how much it's used. You have an increase in kinetic energy. That means you have a positive work done by the net force. You have a decrease in kinetic energy. Net force is applied in opposing to the motion, right? Then you have a decrease in kinetic energy. The object decelerated, slew down. Let me see. This is you're gonna do this in a homework too. But let's say I have a nail. I have a nail. So I'm going to pound the nail with a hammer. Initially, I'm going to pound the hammer with the V initial, this much. Then when I pound it, when I have an initial speed, boom, and then a hammer hits the nail, and this nail will go into the wall for distance D, right? So ignore all the heat, and then you may have to use that energy to change the structure and all that thing. Let's say at this point, ignore those. Then ignore all the other factors. Then the final velocity of the hammer is 0. So change in kinetic energy is going to be 1/2 the mass of the hammer times the V final minus 1/2 mv initial of the hammer. So you lose the kinetic energy, obviously, and that energy is by the nail that opposes. So the nail gives a force onto the hammer, right? I keep using blue. Oops. Nail applies the force onto the hammer in this direction to slow down the hammer and stop the hammer. And then at the same time, it requires this much distance to stop the hammer, right? So this is equals to FD. The force of the nail from the hammer that stops the hammer, and then how much it requires for the nail to go inside by ignoring all the other components of the energy dissipation. But this time, instead of a VI, what if I'm gonna use the same hammer. I'm going to use the same hammer, but I'm going to swung it with 2 times of the initial velocity that I did initially, earlier. So twice more, moving twice faster. How much deeper does the nail go in compared to before? This new distance, how much would that be? Either way, hammer has to stop. To stop the hammer, we were saying that nail is going to apply the force to stop the hammer. And so final velocity, final speed of the hammer is 0. But now instead of initial velocity, same initial velocity, you're moving it with the twice of the initial velocity. So here, in this case, change in kinetic energy now zero, right? So this is 2, it's 0. So it's the same. But instead of a minus 1/2 mvi, now we're going to have a 2 times vi square. You see, this is square. So therefore, change in kinetic energy now is going to be how much difference? It's 4 times because of the square of minus 1/2 mvi square. So this 2, twice of the speed, because of its square, it's 4 times. And this part, right? This minus 1/2 mvi square, this is equals to FD, we said. So, but look, the force that the wall can exert to stop the hammer, it doesn't matter you're moving with the 4 times of the speed, 100 times faster, it's just the property of the wall. So the wall still gives you the same amount of force to stop. But nail will have to go in longer, deeper, because you're only giving the same amount of force. Now, instead of that, it takes a longer for a nail to stop the hammer. So therefore, you see that a new distance, F, and then D prime, the D prime is 4 times than D. So if you hit the hammer with the twice of the speed, the nail will go in, instead of a double deeper, it's going to be 4 times deeper. Because of the, so this is how you can apply work energy theorem. Work energy theorem is the change total work is that equals to the change in kinetic energy, and kinetic energy is 1/2 mv squared. And you might see other example in the class, but for now, this is it. Okay, I'm gonna see you in a discussion.